Most of the time that I spend working on and thinking about the Colorado is sitting at my desk in Seattle, so I'm happy to be here amongst you all that I think share a passion and commitment to the river. We all hear about climate change, it seems like every day or every week now. We hear a lot of the same information but seem to draw vastly different conclusions on the importance, the validity of it. Makes me sometimes question the objectivity of our decision-making process. So I want to touch real quick on the scientific basis, but go real brief on the first three and focus mostly on the implications, temperature, precipitation, stream flow, snowpack, and resulting water resource implications. Start there. The greenhouse effect, we've all heard of it. We all live much happier, or at least much warmer lives because of it. If it wasn't for the greenhouse effect, the temperature outside would be about 30 degrees Celsius cooler. And it's actually a pretty straightforward process. The sun's radiation comes in through the Earth's atmosphere, warms the Earth then re-radiates back out to space. The radiation leaving the surface of the Earth is absorbed by what we call the greenhouse gases, and some of that radiation is then redirected back to the Earth, creating a net heating. Why does that happen? It's a function of three things primarily: the wavelength of the sun and Earth's radiation, the composition of the atmosphere, and at what wavelengths the gases in the atmosphere absorb at. So every body emits radiation, and when I say every body, I mean body, water bottle, computer, microphone, anything that has temperature emits radiation. Temperature is defined as anything above 0 degrees Kelvin. It's absolute zero, so 0 degrees Kelvin is negative 273 degrees Celsius. The wavelength at which a body emits radiation is inversely proportional to its temperature. So I think this is a pointer. The bigger the temperature, the smaller the wavelength. The smaller the temperature, the longer the wavelength. The sun is very, very hot. It's 6,000 degrees Kelvin. So it emits what we call shortwave radiation. If you can see here, the scale is from 0.1 to 100 micrometers. The sun is on average wavelength less than 1 micrometer. The Earth, on the other hand, is relatively cool. It's 288 degrees Kelvin, so it emits what we call long wave radiation. These are the same scales. You can see the wavelength of the Earth's radiation is longer. It's further to the right. The next plot will have the same x-axis. This is the last one of these type of things. So again, this is where our sun was. These wavelengths here. The Earth's radiation on the right at the longer wavelengths. We'll put one of our greenhouse gases up here. This y-axis is the amounts of radiation that this particular gas can absorb. If we look here at 0.2 micrometers, we see that this is the sun's shortwave radiation, that it passes straight through water vapor. Water vapor does not absorb anything at this wavelength. Over here at, say, 90 micrometers, water vapor will absorb 100% of the radiation at that wavelength. So what we can say about that is that in this part here, above in the sun's wavelength, we see that at certain bands that water vapor will absorb incoming solar radiation. We also see here at the longer wavelengths of the outgoing Earth's radiation that water vapor also absorbs radiation. Carbon dioxide, on the other hand, absorbs essentially nothing in the wavelengths of the sun's radiation, yet absorbs at different bands in the outgoing long wave radiation from the Earth. So from carbon dioxide, what we could draw is that increases in carbon dioxide will not keep out any of the incoming solar radiation, but will in fact absorb outgoing long radiation from the Earth. What we'd expect from that then is increasing carbon dioxide would not decrease any incoming solar radiation, but would trap some outgoing long-wave radiation from the Earth. The scale here on the top, the blue is carbon dioxide concentrations, the bottom is temperature, and we see exactly what we'd expect from the last plot, that as carbon dioxide goes up, the temperature of the Earth goes up. Unfortunately, it's not entirely that simple. There are some feedbacks and some uncertainties. Water vapor is the big one. Again, we see that water vapor does absorb some of the incoming solar radiation. If we heat up the atmosphere from increasing carbon dioxide, a warmer atmosphere can hold more water vapor. Therefore, there's going to be more water vapor. We may absorb more of the incoming solar radiation. We are going to absorb more of the outgoing long-wave radiation, but exactly where that balance is, we're uncertain. If you look at it real quick, you can see there's probably more area above the outgoing Earth's radiation, which would make you think that water vapor produces a net heating effect. In effect, it does. It contributes about 1/2 of the current greenhouse effect in the atmosphere. However, there still is uncertainty. If the additional water vapor in the atmosphere is in the form of low, thick clouds, this would actually lessen the warming. These clouds are very effective at reflecting incoming solar radiation. If the increased water vapor would take the form of these high cirrus or alto-cirrus clouds, this would increase warming. The incoming solar radiation passes through this type of cloud, but the outgoing radiation from the Earth is trapped. There's a significant amount of other feedbacks. Maybe the simplest one is the extent of Arctic ice. Incoming solar radiation reflects off the ice. Ice has a very high albedo or reflectivity. Solar radiation comes in, reflects right off, goes back out to space without any heating. If you melt a little bit of that ice, that radiation now comes in. Where it used to bounce off, it is absorbed by the land cover, heats, and resulting will melt more ice. Forest uptake, increased temperatures will mean increased biologic uptake of carbon dioxide, be a negative feedback. Ocean currents are, it's a big heat conveyor belt, but there is significant uncertainty as to those feedbacks. I'm going to go real quick on some observations here. This plot is somewhat repetitive, but it is probably the most famous plot in all of science. The y-axis is the concentration of carbon dioxide in the atmosphere. Before the Industrial Revolution, the atmosphere had about 270 parts per million by volume CO2 concentration, and today we're up around 383. Some make the argument that that's could be natural. It is true, carbon dioxide does vary naturally. However, that happens by and large on geologic timescales for geologic processes. This is global average temperature over the last 150 years. As you can see, the temperature is going up. Started going up about the turn of the century. It's relatively linear, with the exception of the anomaly here around the 1940s that's largely attributed to solar variability. We hear often about sea ice extent. Satellite pictures of the ice caps retreating. What we don't hear as often about is ice thickness. In actuality, we've lost 40% of our thickness of Arctic sea ice in the last 40 years. We hear a lot about glaciers thinning, glaciers retreating. This plot is actually glaciers thinning. You can see there's a couple that are actually getting bigger. If you look just at glacial retreat, I believe that every glacier in the world, with the exception of one on the north side of Mount Rainier, is retreating. This is where temperature increases are happening. These are 1995 to 2004 means relative to 1950. This plot here is somewhat of a record of all the warmest months from 1880 up to 2004. Something that's 0 means that that month would be the average temperature from 1880 to 2004. You can see that all the warmest months have happened in the last 10 years. Just last week, the National Climate Data Center released the data for January of 2007. It was actually pretty big news. These records are usually broken by 0.01 or 0.1 degrees, and unfortunately that wasn't the case this time around. So we see that climate is certainly changing, temperatures are going up. We see why. So the question is, what does this mean for the future? How do we figure that out? We use what's called climate models. Most of us have probably heard about them, and a lot of us, I think, see it as somewhat of a black box, but it is really, it's not that well, it might be that complicated, but at the same time, it's a mathematical model that represents all the Earth's physical processes. It divides the Earth up into certain spatial resolution. There are certainly simplifications, but one thing we can do is set these models up and run them with historic greenhouse gas concentrations, historic solar input, and see how they respond. They should recreate our past climate. If they don't, then we know that something's wrong with them and we shouldn't trust them for what they say for the future. But once we have them to the point of we think they can recreate our past climate, what we can do is, change parameters such as the concentrations of greenhouse gases in the atmosphere. If we increase CO2, we can see how the Earth responds. But real quick, before we go to the future, this is sort of a validation plot. This is the models run with the historic greenhouse gas concentration, so started at 270 here, ended at 380 here, and we see that they're not perfect, but at the same time, they do recreate to a large degree the Earth's climate response, temperature responses to increased carbon dioxide. So if we have models that will react to and show us how climate will evolve if we have increased carbon dioxide in the atmosphere, the question is, we don't really know what our atmospheric carbon dioxide concentration is going to be for the next 100 years. There is an organization called the Intergovernmental Panel on Climate Change, the IPCC. They create projected future emission scenarios. We're looking at the A2 and the B1. The A2 is based on relatively rapid economic and population growth in China and India, continued reliance on fossil fuels. The B1 is sort of a best case scenario. That's America signs on to the Kyoto Protocol, and we start working towards more reliable fuels and that sort of thing. But do remember these two. A2 is the high emission scenario. B1 is the low emission scenario. It's kind of a best case and a worst case scenario, so they're going to be a theme throughout here. So this is the temperature response from these climate models with under each emission scenario. So the A2, the higher emission scenario, we see at the end of a century that the global average temperature increases about 4 degrees Celsius. Under the best case scenario, the global average temperature increases by about 2 degrees. Now, we have a lot of confidence in these models on temperature. You increase carbon dioxide, temperature goes up. The more you increase it, the more temperature goes up. There is variability between the models, but by and large, they show very much the same sensitivities. Precipitation, on the other hand, the climate models are not as good at yet. They don't agree amongst themselves. This is a precipitation map this is the outline of the United States. Up here where it's blue, this is when 15 out of the 18 models say it's going to get wetter. Where it's pink is 15 out of 18 say it's going to get drier. This is the general trend that we've seen around the Earth, increasing precipitation at northern high latitudes, decreasing precipitation along the equatorial or the band around 30 degrees north where the Earth's deserts kind of are, and those deserts moving further north. What's important for us here is that across these models there is very much a zero net change in annual precipitation volume. This is temperature in the Colorado River. The solid dark line is the average across 11 climate models. The top is for the B1 lower emission scenario. A2 is the higher emission scenario. Each individual colored squiggly line represents a different climate model. I used 11 different ones in my study. I won't go into all of them. GISS, the American ones anyway, are the Goddard Institute for Space Studies, the NCAR Parallel Climate Model, and the Geophysical Fluid Dynamics Laboratory. There's a Russian model, there's a British model, Australian, Canadian. So that's temperature changes. If we look at precipitation changes, and these spatial plots are an average across all models, all 11 models. So the top is the B1 emission scenario, the lower emission scenario. And what we see is, a general drying out of the desert southwest. The further out in the century, the more the drying out. An increase in precipitation in the mountainous headwaters. It's interesting to note that the same pattern shows in the A2, but just a little bit more extreme or a little more developed. The actual net precipitation difference over these periods, period 1 is 2010 to 2040, 2040 to 2070, and 2070 to 2100. So 3 different chunks moving out through the century. There is little net precipitation change if you average across all the models. The A2 has small reductions. What's also really important in the Colorado River, really in any river basin, is when the precipitation falls. Temperatures in the winter obviously lower. Precipitation that falls in the winter, a greater percentage of it turns into runoff. And what we actually see is slight decreasing in summer precipitation. These are both for the A2 scenario. And in the winter, we see increases in precipitation. So that bodes well for runoff. Hopefully that can offset some of the temperature effects. This is just when in the year, these are months, January through December, when we expect to see most of the warming. If we just look at, say, the top one, this is the A2 scenario at the end of the century. All models show this pattern, though, but it's the greatest warming in the summer and late summer. Precipitation change, this is, again, increases in winter precipitation, decreases in summer precipitation. So let's move to the implications of those temperature and precipitation changes on stream flow, snowpack, and then the resultant water resource. So unfortunately, we've only gotten here so far, but we'll move quickly. We just developed our temperature and our precipitation signal for the next 100 years. The climate models, as I said, operate on a much larger spatial resolution. They're about anywhere from 2 degrees to 4 degrees latitude by longitude. What we're going to use these precipitation temperature signals for is to run a hydrology model. These run on much smaller resolutions, about 10-kilometer grid cells, so we need to do some downscaling, some bias correction. From these, we generate streamflow sequences that we can then put into a reservoir model that mimics how the operations of the basins happen and get some sort of system reliability. Bias correction downscaling is important, it's involved, but we may not need to talk too much about it here. We'll skip over it. The hydrology model, it's much like the climate model. It represents the processes of the Earth mathematically. You force it with temperature and precipitation, and it gives a time series of temperature and precipitation. So from these climate simulations, we have a daily time series of temperature and precipitation for the next 100 years, and from that we can get runoff. Just like the climate model, before we can really believe what this thing says for the future, we need to see that it can recreate the past. This is a validation plot. The red one is simulated flow from the hydrology model. The blue is naturalized, actually gauge stream flow, but naturalized overlapping period of record. And we see that the model does pretty well. It's not perfect, but so the solid black line here is the average hydrograph at Lee's Ferry from 1950 to 2000. The red line is our 2010 to 2040 stream flow of the same location under the lower B1 emission scenario. So there's a 0% change in net runoff volume, but we can already see some of the effects of